8.6 Resonance Structures. We sometimes encounter molecules and ions in which the experimentally determined arrangement of atoms is not adequately described by a single Lewis structure. Consider the molecule of ozone, O3, which is a bent molecule with two equal oxygen-oxygen bond lengths. Because each oxygen atom contributes 6 valence electrons, the ozone molecule has 18 valence electrons. In writing a Lewis structure, we find that we must have one single bond and one double bond to attain an octet of electrons about each atom. However, this structure cannot by itself be correct because it requires that one single bond must be different from the other contrary to the observed structure. We would expect the double bond to be shorter than the single bond. In drawing a Lewis structure, however, we could just as easily put the double bond on the left. The placement of the oxygen in these two alternative but completely equivalent Lewis structures for ozone is the same, but the placement of the electrons is different. Lewis structures of this sort are called resonance structures. To describe the structure of ozone properly, we write both Lewis structures and use a double-headed arrow to indicate that the real molecule is described by an average of the two resonance structures. To understand why certain molecules require more than one resonance structure, we can draw an analogy to the mixing of paint. Blue and yellow are both primary colors of paint pigment. An equal blend of blue and yellow pigments produces green pigment. We cannot describe green paint in terms of a single primary color, yet it still has its own identity. Green paint does not oscillate between two primary colors. It's not part blue and part of the time and yellow the rest of the time. Similarly, molecules such as ozone cannot be described as oscillating between the two individual Lewis structures shown above. The true arrangement of the electrons in molecules such as ozone must be considered as a blend of two or more Lewis structures. By analogy to the green paint, the molecule has its own identity separate from the individual resonance structures. For example, the ozone molecule always has two equivalent oxygen-oxygen bonds whose lengths are intermediate between the lengths of oxygen single and oxygen double bonds. Another way of looking at it is to say that the rules for drawing Lewis structures do not allow us to have a single structure that adequately represents the ozone molecule. For example, there are no rules for drawing half bonds. We get around this limitation by drawing two equivalent Lewis structures that, when averaged, amount to something very much like what's observed experimentally. Figure 8.12, Resonance. Describing a molecule as a blend of different resonance structures is similar to describing paint color as a blend of primary colors. As an additional example of resonance structures, consider the nitrate ion, NO3-1, for which three equivalent Lewis structures can be drawn. Notice the arrangement of atoms is the same in each structure, only the placement of electron differs. In writing resonance structures, the same atoms must be bonded together in all structures so that only differences are in the arrangement of electrons. All three Lewis structures are taken together adequately describe the nitrate ion, in which all three nitrogen-oxygen bond lengths are the same. Resonance and benzene. Resonance is an extremely important concept in describing the bonding in organic molecules, particularly in the ones called aromatic molecules. Aromatic organic molecules include the hydrocarbon called benzene, which is the molecular formula C6H6. The 6 carbon atoms of benzene are bonded in a hexagonal ring, and the one hydrogen atom is bonded to each carbon atom. We can write two equivalent Lewis structures for benzene, each which satisfies the octet rule. These two structures are: each resonance structure shows 3 carbon-carbon single bonds and 3 carbon-carbon double bonds, but the double bonds are in different places in the two structures. The experimental structure of benzene shows that all 6 carbon-carbon bonds are of equal length, intermediate between a typical bond length for carbon-carbon single and double bonds. Benzene is commonly represented by omitting the hydrogen atoms attached to the carbon and showing only the carbon-carbon framework, which is with vertices unlabeled. In this convention, the resonance in benzene is represented either by two structures separated by a double-headed arrow, as with our other examples, or by a shorthand notation in which we draw a hexagon with a circle in it. The shorthand notation on the right reminds us that benzene is a blend of two resonance structures. It emphasizes that the carbon-carbon double bonds cannot be assigned to specific edges of the hexagon. Chemists must both use representation of benzene interchangeably. The bonding arrangement in benzene confers special stability to the molecule. As a result, literally millions of organic molecules contain the six-member ring characteristics of benzene. Many of these compounds are important in biochemistry and pharmaceuticals and in the production of modern materials. We'll say more about the bonding of benzene in Chapter 9 and its unusual stability in Chapter 25.